Hello everyone and welcome to the first of the statistics video lecture series. My name is Professor Hunter, and just as a couple of disclaimers before we get started, one is that I apologize in advance for any technical glitches that you might see in this video. The stylus I am working with is not the best and it does glitch sometimes. And these subtitles are auto-generated and may not always exactly match what I am saying, but I'm doing the best that I can with the limited time and technology that I have. So for this video lecture, if you go on Canvas, you can find this exact same PowerPoint to follow along. I also posted the blank note outline that you would have received if this were a face-to-face class. So please feel free to follow along with the video lecture and take notes in the blank note outline as you normally would in class. To give you additional help and kind of help you transition to the online format, I have also posted a completed note outline on Canvas that contains all of the blanks filled in and all of the examples filled in. So between these resources, hopefully we will do the best that we can to simulate an actual face-to-face class in an online format. If you want to, at any point during this video, attempt a problem before I do it, just feel free to pause the video and then resume when you are finished working, but I will be going through all of the examples one right after the other. Also, because this is a public video, comments have been disabled, so if you do have a question on the video, please send me an email with the video in question, and if it's a specific question, please include a timestamp and I will be happy to answer any questions that you have via email. So for this section, please make sure that you do the Price is Right activity first, because that will give us an introduction into what exactly a confidence interval is. The Price is Right activity is posted on the Canvas page under the Chapter 6 module. So what we're going to be doing in this section is we are really going to be using sample data to draw conclusions about populations. Specifically, we are going to be using sample statistics such as sample mean to estimate population parameters such as population mean, because that's the whole point of statistics, is to use something like a sample mean to estimate an unknown population mean. So we have a couple of different types of estimates for population parameters. One is called a point estimate, and a point estimate is a single value that is used to estimate a population parameter. And the most unbiased point estimate for the sample mean the most unbiased point estimate for the population mean is the sample mean. So remember that the mean of all possible sample means equals the population mean. That is why this is called an unbiased estimator. So for this first one, let's say that an economics researcher is collecting data about grocery store employees in a county. And this data lists a random sample of the number of hours worked by 40 employees from several grocery stores throughout the country. And what we're going to do is we're going to find a point estimate for the population mean mu. And for something like this, you can absolutely use a calculator. Now, I don't have the emulator software installed on my computer as of yet. By the way, this is what I mean by my stylus glitches. As soon as I get that installed, I will be showing you calculator steps, but we have covered how to find sample mean in class. You enter this data into L1 and you use the 1VAR_STAT option. Or you can just add them all together and divide by 40, since there are 40 employees and our sample size n is equal to 40. So either way, either by hand or on a calculator, you get a sample mean x bar of 29.6 hours. Now, a sample mean is a point estimate of a population mean. It is a single value that is used to estimate an unknown population parameter. In this case, the population mean would be the mean number of hours worked by all grocery store employees in the country. And while 29.6 is probably a pretty good estimate, the likelihood that the population mean is exactly equal to the sample mean is virtually zero. I mean, the odds that that population mean was exactly 29.6 is pretty much near impossible. So instead of estimating the population mean to be exactly equal to the sample mean, we will estimate that mu will lie in some sort of interval. So instead of saying that, okay, we estimate that the population mean is exactly 29.6 hours, we would make a statement of, the sample mean is somewhere between 28 and 30 hours, something along those lines. That is what is called an interval estimate. An interval estimate is an interval or range of values that is used to estimate a population parameter. So even though the population mean will not be exactly equal to the sample mean, it's probably pretty close because the sample mean is an unbiased estimator for the population mean. So the sample mean is not completely useless. It is probably pretty close to what the actual population mean is. So we're going to use the sample mean x bar to form our interval estimate. So to form the interval estimate, we're going to use that point estimate as a center of our interval, and we are going to add or subtract what is called a margin of error. So to determine the margin of error, you first need to figure out how confident you need to be that your interval estimate actually contains the value of the parameter, because there's always that small likelihood that your interval estimate won't actually contain the real population mean. So you need to set what is called the level of confidence. So the level of confidence is the probability that the interval estimate will actually contain the population parameter, assuming that this estimation process is repeated a large number of times. So if you remember from the central limit theorem that as long as the sample size is at least 30, the sampling distribution of sample means is a normal distribution. So the level of confidence, which we're going to denote by the variable lowercase c, is the area underneath the standard normal curve between two critical values, which we're going to denote as ZC and negative ZC. These critical values, they're z-scores. These critical values separate sample statistics that are probable from sample statistics that are unusual or improbable. So these two critical values are going to be z-scores, and they're going to be symmetric. They're going to be on opposite sides of the center, z equals 0. And the area between these two z-scores will be equal to the level of confidence as a decimal. So for example, what we're going to do is we are going to find the critical values for a 90% confidence level, and we are going to draw diagrams for this. So a level of confidence of 90% means that you want a 90% chance that the interval estimate that you make for the population mean will actually contain the population mean. So the level of confidence is actually going to be the area underneath the standard, oh my goodness, let's try this again. It is going to be the area underneath the standard normal curve. I give up. I give up. This is supposed to be a bell curve. Between two critical values, which we're going to denote as negative ZC and positive ZC. Now, the level of confidence as a decimal would be 0.90, so that means that the area between these two z-scores is 0.90, the level of confidence. The level of confidence is the area underneath the standard normal curve between these two critical values, ZC and negative ZC. So that means that the area to the left and of negative ZC and the area to the right of positive ZC need to be what's left over. If you remember, the total area underneath the standard normal curve is equal to 1. And remember that these are symmetric. They are on opposite sides of the z equals 0 in the middle. So because of that, if you do 1 minus 0.90 and then you divide that by 2, you're going to get 0.05. So 0.05 is going to be the area in each of these tails. So this tail will have an area of 0.05, and this tail will have an area of 0.05. So what we have are areas underneath the standard normal curve, and we are looking up z-scores that go with that area. So the table that you are going to use is you are actually going to use the inverse standard normal table. I am so sorry for this stylus. I don't know what is wrong with it, and nothing I have done so far has been able to fix it. So anyway, you're going to use the inverse standard normal table. Now remember, the inverse standard normal table only ever deals with areas to the left. And we have two z-scores to look up. Keep in mind, though, that they are symmetric. So let's actually start with this one. Let's actually start with negative zc. The area to the left of negative zc is 0.05. So if you look up 0.05 in the standard normal table, you get a z-score of negative 1.645. So negative 1.645 is the negative ZC. That is one of your critical values. Now remember that these two critical values are on opposite sides of 0 and they are symmetric. So without even doing any work, the positive z-score, positive ZC, is going to be positive 1.645. So your two critical values, negative ZC is going to equal negative 1.645, and positive ZC is going to be positive 1.6. Positive ZC is going to be positive 1.645. Now, once your critical values have been found, you have to keep in mind that the level of confidence is not a 100% guarantee. So the difference between the point estimate and the actual value of the population parameter is what is called the sampling error. So the sampling error is that difference between whatever the sample mean is and whatever the actual population mean is. However, keep in mind that as you take different samples, you're going to get different sample means for each different sample. So what margin of error is going to be is it is going to be the maximum amount of error that you want to allow given a certain level of confidence. So definitely this formula here is extremely important, and you definitely need to, highlight this, remember it. This is the margin of error formula for these levels, so for these confidence intervals. I'm sorry, I'm distracted by the amount of technical problems I'm having. I'm very sorry. So, given a level of confidence C, the margin of error, which we're going to denote by the variable uppercase E, which is sometimes called the error tolerance, is the greatest possible distance between the value of the actual population parameter and the point estimate. Now, this is actually really important. If the population standard deviation sigma is known, then the margin of error is going to be the positive critical value ZC times the population standard deviation sigma divided by the square root of sample size, provided that the sample is random and either the population is normally distributed or the sample size is at least 30. That is from the central limit theorem. So what we're going to do is we're going to use that data from that first example, the grocery store employees. We're going to assume that we are setting a 95% confidence level, and we're going to find the margin of error for the mean number of hours worked by the grocery store employees. And we're going to assume that, perhaps from previous studies or something, that the population standard deviation is 7.9 hours. So sigma was 7.9. And if you remember from when we found the sample mean from the first example, the sample size was 40. There were 40 grocery store employees sampled. So let's start with the 95% confidence level. So for the confidence level, that means that the area underneath the standard normal curve between these two critical values, negative ZC and positive ZC, is going to be equal to the level of confidence as a decimal, which is 0.95. So we need to actually look these up first. Now remember that the total area underneath the standard normal curve is equal to 1. And remember that these two tails, to the left of negative ZC and to the right of positive ZC, are going to be the same. The tails are symmetric. So to find the area of each of the tails, you're going to take 1 minus 0.95, which is 0.05. Remember, that's the area of the two tails put together. If you divide it by 2, you get the area of each individual tail, which is 0.025. So the area of each individual tail is going to be equal to 0.025. So that tail right there is 0.025. And this tail right here is going to be 0.025. So if you have an area underneath the standard normal curve and you need to find the z-score that goes with it, you're going to use the inverse standard normal table. Now the easiest of these two critical values to look up in the inverse standard normal table is actually negative zc, because the area to the left of negative zc is 0.025. So if you go look up 0.025 in the inverse standard normal table, you get negative 1.96. Now, because these two tails are the same and these two z-scores are symmetric, you don't even need to do any work to find the other critical value. So the other critical value, positive zc, is going to be positive 1.96. So, since the population standard deviation is known, we're going to use the margin of error formula that involves population standard deviation. So the margin of error is going to be the positive critical value zc times the population standard deviation sigma divided by the square root of n. So the formula involves the positive critical value, so positive 1.96 here is what we're going to be using. So the margin of error is going to be zc 1.96 times the population standard deviation, which was given to us as 7.9, divided by the square root of the sample size, so the square root of 40. Now, if you type all of this into a calculator, you should be able to do it all at once, and you should get a margin of error of about 2.4 hours. So your margin of error is 2.4. So what this means is that from sample to sample, if you were to take multiple samples of all the same size 40, you would allow a maximum error of 2.4 hours, which means for every single sample that you take out of this population, you're going to allow a maximum difference of 2.4 hours between the sample mean and the actual population mean. So for the actual confidence intervals are the interval estimates for confidence intervals is just another name for an interval estimate. So to construct an interval estimate for a population parameter, you're going to use both the point estimate and the margin of error. The point estimate for population mean is sample mean x bar. This interval estimate is what is called a confidence interval. So confidence intervals, interval estimate, they pretty much mean the same thing. We're going to call it a confidence interval. So a confidence interval is an interval estimate for an unknown population parameter. So the confidence interval for a population mean mu is going to be this. So interval estimates are, we're estimating mu is going to be between this value and this value. So to construct the confidence interval, you're going to put the population parameter, in this case mu, in the middle. And then for the low end of the interval estimate, you're going to take the sample mean x bar and you're going to subtract the margin of error. That will be the low end of your estimate. Now for the high end of your estimate, you're going to take your sample mean x bar and you're going to add the margin of error. So you will estimate that the population mean will be between x bar minus e and x bar plus e. So you'll have a low end, which is x bar minus e, and a high end, which is x bar plus e. So here in words is how to construct a confidence interval for a population mean. Now it is important to assuming that the population standard deviation sigma is known. If sigma is not known, that is going to be another section. It has an entirely different process. So this first step here is actually extremely important. You have to make sure that you actually know sigma. So if you know sigma, you're going to use the margin of error formula that involves sigma. If you do not know sigma, do not use the margin of error formula that uses sigma. So just make sure that you are given the population standard deviation sigma first. Then you're either going to find the sample statistics n, sample size, and x bar, sample mean. If you are not given the sample mean, you're just going to find it as normal by adding all of the x values together and dividing by the sample size. Then you are going to find the critical value that corresponds with the given level of confidence. So the critical value that you are going to actually use is the positive critical value, so positive ZC. You can look up negative ZC just to get to this point, but you're not going to use negative ZC in the margin of error formula. You're only going to use positive ZC. Then you're going to calculate the margin of error E. So the margin of error is going to be that positive critical value ZC times sigma divided by the square root of n. Then you're going to find the left and right endpoints of your interval estimate. So your population parameter that you're estimating is going to go in the middle. For the left endpoint, or the low end of your interval estimate, you're going to take the sample mean, subtract the margin of error. And then for the right endpoint of your interval estimate, or the high end of your estimate, you're going to take the sample mean x bar and add the margin of error. So we're going to use that grocery store employee example that we've been kind of working on this whole time, and we're going to use the work that we've done so far to construct a 95% confidence interval for the mean number of hours worked by all grocery store employees in the country. So from that first example, we calculated the sample mean to be 29.6. And from the example that we just did, we got a margin of error of 2.4 hours. So the confidence interval with a 95% level of confidence is going to go something like this. The population mean, that is what we are estimating, is going to be between x bar minus E and x bar plus E. So x bar minus E is going to be the left endpoint of your interval, and then x bar plus E is going to be the right endpoint, with mu right in the middle here. So we're going to take our sample mean, 29.6. We're going to subtract the margin of error, 2.4. Mu is going to go in the middle. And then we're going to take the sample mean, x bar, 29.6, and we're going to add the margin of error, 2.4. So the population mean, if you do 29.6 minus 2.4, is going to be 27.2. And if you do 29.6 plus 2.4, you get 32.0. So this is your confidence interval, or your interval estimate. So in context, what this means is that with 95% confidence, we can say that the population mean number of hours worked by all grocery store employees is between 27.2 hours and 32 hours. So let's do another one, and we're going to start from scratch for this next one. So let's say that a college admissions director wants to estimate the mean age of all students that are currently enrolled. So we are going to be eventually estimating population parameters other than mean, so just make sure that you are keeping track of what exactly you were asked to estimate. We are estimating mean age, so we are estimating mu. In a random sample of 20 students, so your sample size n is equal to 20, the mean age is found to be 22.9 years. So because this 22.9 is in the same sentence as sample, this is your sample mean. So your sample mean, x bar, is 22.9. From past studies, the population standard deviation is known to be 1.5 years. So sigma is equal to 1.5. And the population is normally distributed. That's actually pretty important. We're going to construct a 90% confidence interval. So your level of confidence, C, is going to be 0.90 for the population mean age. So now that we have all of our given information, we know sigma, so we're going to use the margin of error formula that uses sigma. And we're going to, we already given the, I'm sorry about that. So we are already given the sample mean of 22.9, so we don't have to calculate that ourselves. So let's actually just jump into using the level of confidence here to find the critical values. So if your confidence level is 0.9, that means that the area between these two critical values, negative ZC and positive ZC, is going to be equal to the level of confidence, which is 0.9. So remember that the total area underneath the curve is equal to 1. So if you do 1 minus 0.9 and then you divide that by 2, you get an area of each individual tail to be 0.05. So this tail right here is 0.05, and then this tail right here is 0.05. So the easiest critical value to look up in the inverse standard normal table is the negative ZC. So if you look up 0.05 in the inverse standard normal table, you get negative 1.645. And then remember that these two tails are symmetric and these two critical values are symmetric. So positive ZC is going to be positive 1.645. So critical value ZC is going to equal 1.645. Next, after you find the critical value that goes with your level of confidence, you're going to then construct the margin of error. So because we know the population standard deviation sigma, we are going to use the margin of error formula that uses sigma. So the margin of error is going to be the critical value ZC times sigma over the square root of n. So we're going to take that critical value we just found, 1.645. Then we're going to multiply it by sigma, which was given to us as 1.5, divided by the square root of the sample size, so the square root of 20. So then when you calculate all of that, you get a margin of error of approximately 0.6. So then we're going to construct our confidence interval. So our confidence interval on the left endpoint is going to be x bar minus the margin of error E. And then on the right endpoint is going to be the sample mean x bar plus the margin of error E. So for our left endpoint, we're going to take our given sample mean, 22.9, and we're going to subtract that margin of error that we just found, 0.6. Then on the right endpoint, we're going to take that sample mean that we were given, 22.9, and we are going to add the margin of error, 0.6. So on the left, if you do 22.9 minus 0.6, you get a left endpoint of 22.3. And then on the right, if you do 22.9 plus 0.6, you're going to get a right endpoint of 23.5. So what this means in context is that with 90% confidence, we can estimate that the mean age of all students at this college is between 22.3 years and 23.5 years. So mu is going to be between I give up. It's between 22.3 and 23.5 years. Now, here's the thing about level of confidence. If you were to do that exact same problem again with a 95% level of confidence or a 99% level of confidence, you would find that the interval estimate actually gets wider. So as the level of confidence goes up, the interval estimate gets bigger because it just becomes kind of a catch-all. All right, we're going to make this estimate really big so that, it's not exactly accurate, but the population parameter is probably in there somewhere. And that's just how level of confidence is. As the level of confidence increases, the confidence interval widens. The wider the confidence interval, the higher success rate that the population mean is actually going to lie in that interval. However, as the interval estimate gets wider, the less accurate it becomes. It's not exactly a pinpointed estimate anymore. It's really more of a catch-all. So if you want to improve the precision of your estimate without decreasing the level of confidence, the only way to do that is to increase the sample size. So if you want a narrow interval estimate, but you want a high level of confidence, the only way to do that is to sample more people, is to increase the sample size. So if you know that you want to have a specific margin of error, there is a way to determine the minimum sample size needed to guarantee a certain level of confidence and a given margin of error. So this is the minimum sample size needed to estimate the population mean mu given a specific margin of error. And this is the margin of error formula just solved for n. So n is going to equal ZC times sigma over E. And then the entire thing is going to be squared. Please note that this exponent is outside the parentheses because everything in the parentheses is getting squared. So if you're typing this into a calculator, make sure that your exponent is outside the parentheses. So let's say that the economics researcher from the grocery store example wants to estimate the mean number of hours worked by all grocery store employees of the country. We're going to figure out how many employees must be included in the sample for you to have a 95% confidence, and we want to be 95% confident that the sample mean is within 1.5 hours of the actual population mean. So we want to guarantee that the difference between the sample mean and the population mean is always going to be within 1.5 hours. So that is our given margin of error. We want our margin of error to be up to 1.5 hours, which is kind of a small margin of error. So with a level of confidence C of 0.95, we need to find the critical value that goes with this. We've already done this one, so the critical value positive ZC that goes with a level of confidence of 0.95 is 1.96. And from the grocery store example that we did a couple of examples ago, it did give us that the population standard deviation sigma was 7.9. So the minimum sample size needed to guarantee this margin of error with this level of confidence is going to be the critical value ZC that goes at that level of confidence times the population standard deviation sigma divided by the margin of error, all squared. So we're going to take our ZC, which we found was 1.96. Then we're going to multiply it by the population standard deviation, which the problem gave us as 7.9. Then we are going to divide it by the given margin of error, which is 1.5. And then we are going to square the entire thing. And if you type this in exactly like I have it written, so parentheses 1.96 times 7.9 divided by 1.5 parentheses squared, you will get this as your initial number. So your calculator is going to initially spit out 106.56. However, this is number of employees or people, so we should always round up to the nearest whole number. With minimum sample size, the bigger the better. So if there is anything following the decimal point and you are surveying, people, always round up no matter what is after that decimal point. So you're going to round up to the nearest whole number. So what this means is that to guarantee that with a margin of error of 1.5 hours with a 95% level of confidence, you need a minimum sample size of 107 employees. So that is it for section 6.1. I am very sorry for the amount that the stylus was glitching, and I'm hoping that it is still legible. If it wasn't, remember that the completed note outlines are posted on Canvas, so you can reference those as well if anything was hard to make out. If you have any questions on this video, please feel free to email me, and I will do my best to answer your question via email. So thank you all very much for watching, and I will see you in the next video for section 6.2. Confidence intervals where sigma is unknown. So thank you for watching, and I will see you in the next one.